Hi, everybody. My name's Dermot O'Shea, and I'm the host of the Antenna podcast. And today I'm delighted to have Olivier Robin. Olivier, would you like to introduce yourself?
Thank you, Dermot. Olivier Robin at Taoglas. I'm currently the COO, overlooking those sexy products we are designing here at Taoglas, including antennas, speakers, and advanced RF components.
Well, I think we have to start right there, Olivier. You call them sexy products. Like most people walking down the street would say, "What the hell is sexy about an antenna?" So please tell us why you think antennas are sexy.
Well, so usually when in this electronic world, everybody's talking about their own products in a very technical terms. It's either very electronically or very electromagnetically or very mechanically the approach that people use to talk about their products, whether they are salespeople or engineers. What I noticed in the last 25 years is that if you come up as a supplier, I've always been a supplier. I was never on the customer side, but when as a supplier you show up at a meeting with a customer or with all the standard distributors, the famous 10 distributors that a lot of people work with. They usually want to see a different approach and something a bit out the norm. That's where initially in the past we used the word black magic and make slides about black magics and talking about antennas through those themed PowerPoint slides. Also trying to convert the dialogue that we use on a daily basis into a more visual, a more understanding wording relative to the antennas. So, for example, we know that we are using the LDS antenna, the LDS technology today, laser direct structuring. This is a very cool way to make 3D antennas. They look nice. They look golden plated, very light because they're on plastic. So instead of introducing, this is one more technology that we have and we can put plating on, so instead we will go to a customer and have existing products that we have made looking really outside the standards so that people actually bite it and say, hey, wow, this is cool or sexy. And usually that's the way they remember about who you are or about the company you represent. So, and I like, and to be fair, I also like to use the word sexy because usually it triggers a big smile to their faces too. So they always want to know more. So I guess that's where it's coming from. Trying to get the interest, trying to get the moment we spend with a customer memorable for hopefully for us, but for them too. And then they give them the hopefully the need to call us back for maybe converting into a real project from those few slides or those few meetings we had with them. So I would say this is really where the sexiness comes from. We also have, LDS antenna technology is a part of it, so that applies to embedded antennas. For external antennas, we can also speak about sexiness in a way that you very often need to design an antenna housing that's actually attractive too for the customer. So the aesthetic of the antennas that are on a rooftop or on an ATM machine or a vending machine or on a truck, they kind of need to be as small as possible, but also looking something not like all the other competitors. It cannot just be a big block or a big cube or a big cylinder. And, hopefully the Taoglas product shows that we are not like that, and we bring that sexiness level to the product and the outlook of them. So,
Yeah. It sounds cool when you say it. Probably with my accent, it probably comes as a little bit creepy. But like myself, it doesn't sound like you're from Texas. Where did you grow up, and how did you get into antennas in the first place? Like, is it something you loved when you were a kid, or when
Well,
did you come
so
across them?
I believe we all tried when we were, 10 years old, trying to talk to other people with, you remember the old yogurt pots that you would wash in and put a rope in between them and talk to your sister or brothers on the other side of the house.
The can of
Exactly. So
beans,
it
yeah.
didn't work very well. So I think we also all tried the cheap walkie-talkies that at the time our parents could afford, and it didn't work very well at that time. So I'm not gonna say I was a nerd and trying at 10 years old to redesign a walkie-talkie in my room, but the no, I just fell in love with it. After when I was 18 years old, going to before the engineering school, we had to do some high-level classes of math, physics, and chemistry, where we learned all the whole antenna theories, electromagnetics, Maxwell equations, which was pretty advanced and interesting. During the engineering school, I had a fantastic teacher called Mr. Jekyll, who was he looked a little bit like you, by the way, Dermot. I mean, he was a PhD in antennas. He had studied antennas all his life. He had taught thousands or a few hundreds of PhD students into antennas or EMC, and then he was always talking to customers. So he was not one of your typical teacher where that's what I learned in school 50 years ago. This is the book, and those are the formulas, and please do the exercise, and actually, we compare the results, and that's all. He always had funny stories around antennas, around the submarines, around the soldiers on the field having to deploy antennas and having weird ways to do it better and to improve antenna efficiencies on the field when you have nothing to play with except a pair of scissors and a knife and some barbed wires. So he made it sound like there was money to make in electromagnetism at the time, or EMC or antennas. The classes were cool. I was lucky to be in a school where we had an echo chamber and an acoustic chamber as well. So we actually could build our own antennas with copper tape and plastic parts and measure it. And you realize that could be easy to make your own antennas. So that's what happened. And then when I graduated, he offered me I passed an extra degree called DEA, where without which you cannot even start a PhD. So I passed. I was second out of 50 students, and so it gave me a potential to have a scholarship, which was big at the time. It was 6,000 francs per month, which is a bit less than 1,000 euros today. But for a student, that was a lot of money at the time. Unfortunately, so I did this. He gave me a position in his lab as an engineer, PhD junior and engineer, to work with his university PhD students. And the first job was to work on antennas for submarines for the French Navy. So I thought that was pretty cool to go from very simple ceramic patch antenna formulas to what the hell do we do on a submarine where it's a big metallic box underwater, and it's against any principles and any formulas you learned in school. So that was a very cool job. But then very quickly, as he was very business minded, he liked to develop and study antennas, but his lab could only function with fundings from the Navy, from the Air Force, from all these big teams there that had money and fundings at the time. The cell phone business in 1998, 1999, 2000 started to take off. So we only had, remember, we only had Alcatel at the time, Sagem, Philips, Nokia just started. Ericsson was there a little bit at the beginning. And then suddenly all these companies needed contractors, consultants to develop the new systems, the new cell phones, the new antennas, the new displays, the new all this, right? So it started to get a lot of money flowing from Qualcomm at the time. That they were studying the first DECT cell phones and the multi-band cellular antenna cell phones. So I had the chance to work with a PhD a guy, my colleague, to actually use our own FDTD software developed by the university and simulate the whole cell phone and how to place antennas around the cell phone at the time, because we knew nothing about cell phone. It never existed before. So, and doing the full parametric studies on antennas on a cell phone, which was obviously far from a submarine, but he managed to get waivers from the Army to allocate different engineers to work also on other things so that he could bring more students, etc., etc. So that's the story on my small career. Started 25 years ago about antennas that I had no idea I would do that one day. So and then
Yeah.
and then it kept, I never left that world, because it's always, through all the companies I worked with, there was always a new technology that you had to work for. There was always this brand new equipment, like the MVG anechoic chambers that came up in the 1999 2000. There were brand new measurement systems. Then we had I had as an engineer, the opportunity to work with the SAR and the hack robots, the DAISY systems for SAR and hack measurements. That was also, you never studied this in school because it didn't exist, right? Yeah,
Right.
and then something not neglectable for engineers. When you are 25 years old, you don't expect to be able to even think of or be able to patent something. And at this time, nothing existing about cell phones. So every simple idea you had to improve the antenna size, to shrink to use new materials, to shrink the antenna size, to use ceramic in a cell phone, to optimize the RF budget and the TX chain or the RX chain. It gave you multiple ways to apply for patents, which I did as well. And so all this environment, completely new, very young, very cool products, made me discover antennas more and like antennas. And that's where we are today. And even today at Taoglas, we in almost every design we do, there is always this edge where we haven't been there yet, but we can. And now we have new materials, we have new manufacturing techniques. The machine costs went down. So there is always something we learn with new suppliers, with new partners, with new engineers, with new technology. Simulations have changed dramatically as well. I was lucky enough to use probably the first CST release for Nokia at the time, and all the suppliers were forced to use it. I mean, look at CST today, 25 years later. It's amazing. I mean, it looks like, it's not AI yet, but it looks like you just import a file. It does the mesh automatically. You have to find a few tricks here and there, and it gives you the results super quick. It's amazing how things have changed in 25 years.
No, that's really interesting, and lots of questions there, even already based on what you said, even though I think you only talked about the first quarter of your career. But you mentioned, like, when you were, it sounds like you had a great influence in university. But you mentioned the theory there, right? And that guy seemed to have more practical experience. Like, there's a lot of theory behind antennas, and you mentioned it being a black art. But like, what would you say like is more important? Because you mentioned CST and simulations as well, and then you have the practice and you described greatly some of the things that, why you think antennas need to be sexy. For example, in the practical real world, making them look good on an ATM or on a vending machine, which we
Right.
know is very important. like what percentage, like is the theory important? How important is it? Do I need the theory first? Can I just like Google the theory part and focus on the practice part? Like talk to maybe a kid that's starting out today, and like what would you advise them there on how to
Yeah,
tackle the
so
theory?
so what's very interesting for an RF engineer. So I was never good in mechanics. I didn't like it, and I never grew up in a house where we had all these tools and all this, to fix your bike or motorcycle at the time. I didn't think I could do any mechanic. I could not fix my car. I'm not good enough for that. But the cool thing about antennas,
When
yeah,
you got a puncture
yeah,
once,
yeah. We actually, I mean, you and me, we had, yeah, we and two other colleagues, we had to change the tires, and it took us 2 hours. Four engineers in the car, and it took us
okay.
2 hours. So imagine changing the engine. But no, the cool thing about the antenna job really is there's a big chunk of skills you acquire once you have done all these mock-ups, all these prototypes. We call it integration of the antenna, which is a pure electric part into a mechanical device, or even on top of a rooftop. If the rooftop is not flat, you need to accommodate the shape of that rooftop into the design of your antenna, knowing that very often antennas do not like ground or metal in the vicinity. So today, there's a little bit of theory that you apply on a daily basis. It helps you to understand why is this part needs to be further from the ground, why this part needs to be longer than the other one. But antennas are all about coupling, surrounding elements, and that's something you never study in class. That's something you never learn in a book. It's all about, I've suffered so much doing SAR testing and hack testing and solving SAR problems, that you realize your skills in EMC, electromagnetic compatibility classes, that you learned at the time that you thought was crazy. Well, the noise, the currents running on a PCB, it's something you cannot visualize easily, but with the time you learn that it's never too good to have a speaker with long wires running under an antenna or inside or on top of an antenna. You learn that a keyboard, the lines that connect the keyboard footprint sometimes on a PCB on cheap phones, are actually sucking the RF power and bring all that power back to a place where it doesn't need to be, but it sucks the efficiency of your antenna. So all that practical theory you don't find in a book. I mean, unless there are a few books that came out in the last 10 years, but that's what you learn on the field. And then in the opposite, all the Maxwell equations, all the even the TEM modes, for those who know what this is, into the ceramic patches, you don't typically use it on a daily basis, because we already have so many standard products that we know work well. Most of the time we just spent in fine tuning that new prototype to accommodate a new frequency band or a better axial ratio, or a different level of polarization, for example. So we never, I think the formulas, the big theory is really good when you start a complete new concept and trying to go to converge to a solution quick, but with some strong technical base. But on the daily basis, when you do a GNSS antenna and you just need to add a little bit more bandwidth or better action ratio, you just play with the parts that work already, 80%, and then you spend the 20% of time to fine tune it for the new spec or the new customer or the new surrounding. So I'm not sure if I think I answered the question, but
Very thoroughly, yeah. You mentioned something though in there, SAR, specific absorption rate, that people may not have heard of before. Maybe give us the what definition that is, and how it relates to what it sounded. It sounds like that gave you great training on the learnings of
yeah.
practical antenna design, was
Yeah,
those SAR challenges.
so SAR and hack. Hack is a hearing aid compatibility. This is for the people who wear a little hearing aids, and of course, when you bring a phone close to it, if it's not tuned correctly, it's going to couple to the coil inside the hearing aid, and it's going to make a buzzing sound. So basically, the funny part of designing antennas for cell phones is your job as an antenna engineer until that came up was get as much efficiency as possible, so you get as much power from the radio as possible, so you transmit and receive so you transmit as much power as you can out of the phone, and then you receive as much power as you can from the base station. Okay, and that was easy especially when it was only one band or two bands 25 years ago. Now it's a bit more difficult with the whole 5G spectrum. However, when you send too much power out of the phone, it goes, guess where? Into your head. So your head has an average epsilon of 80, I think. That's a long time ago. I don't remember, but our head is full of water, more or less, and tissues, and the epsilon is really high. And then on one, you have your head, your phone on your head. You have a lot of air, which has an epsilon of 1 on one side, and a big sphere with an epsilon of 80 or 50 on the other hand. So all the power you send from the antenna inside the phone goes right into your head. That which is obviously not good. And the whole SAR studies show that we don't want to have the electromagnetic waves getting too deep into your head, because it could affect the parts that are, mostly the brain parts that are supposed not to be affected by anything, right? So you want to make sure you need to optimize the output power of this antenna into your head to make sure you don't send too much RF and too much current into your head. So now the SAR system came up where we had fake bodies with liquid inside that mimicked the human body behavior at low frequencies and high frequencies. There is a probe that comes inside that fake phantom, and you put the phone along touching the ear on the fake head, and you check inside the fake brain how much power you send into it. So the job as an RF engineer became very tough, because now you need to optimize the antenna in the phone to radiate as much power as possible, but you also need to make sure you comply with the standards as to not sending more than, if I recall now, I think it was 2 watts per kilogram in Europe and 1.6 watt per kilogram in US. Because at the time there was CDMA and different than the GSM standard. So of course, all this needed to be measured, because there is no way you could guess. Now simulations are better. You can, you can import a full form factor. You can put the antenna in there, simulate the body, and find out a bit earlier what could be the SAR level inside the head. But that was tough for the RF engineers to do those jobs. And then the hack levels for the hearing aid compatibility level is the same. You want to, again, get as much E field and H field out of the antenna inside the phone, but you want to minimize the magnetic field that will couple with the hearing aid if a person should wear the device to hear better. So very tough job, tuning an antenna, integrating it into the phone, make sure it radiates as much as possible E field, H field, but also limit those field strengths to not disturb the environment, which is very often the human body. And of course, once you start wearing, that's thanks to that process, the Bluetooth AirPods or hearing aids came up, because at 2.4 gig, the power that goes through your head is not as strong as a GSM signal or a CDMA signal. And if you wear your phone on your belt, if it's a body worn phone, it's not as bad as well than on your head. So all these standards came, in the last 10, 15 years, making the antenna engineer life a little bit more tricky, and also a lot more investments for the antenna companies, because now you have to buy those machines and make sure you deliver products that are compliant.
Yeah. Even the body parts, the speg parts, is it that we have the heads and the hands? But I actually met somebody in the industry that used he was required to do some testing for a pet tracker and used salt water to simulate the body part. I don't know how close that is to real life, but there you go. And antenna engineers are very creative at being able to, mimic the real life installation scenarios. For example, I found how creative we can get. People in Taoglas have been at, like, making fixtures or simulating real life environments that can also fit in the chamber, and give the customer, like, very accurate results of what things are going to
Yeah,
look
and
like in real life.
buying
So
3D printers, the 3D printers saved our lives a few times too. You can create your own jigs for production as well. You can design parts very quick to help you make a prototype overnight. So it's definitely, that's why I said earlier, mechanics is a big part of the antenna RF engineering world. You cannot design an antenna without the mechanical engineer, and vice versa. The mechanical engineers cannot design an antenna without the RF skills behind. So it's really a two-man's job for each antenna, really.
So you mentioned one really interesting project when it was the antennas for the
Mm-hmm.
French submarines. I hope that's not the reason Australia cancelled that submarine order on France. But how do you simulate that environment, and how? Tell us more about that project. Like, how can you communicate with something that's down that far? Like, what
Well,
kind of range
well,
can you
it's
get,
very,
etc.
yeah, it's a long time ago, so I guess it's probably, at least what I know is not secret enough that I will disclose any details. But a submarine is very, very interesting. It's like a metallic box. You have on the flanks, left and right, I believe, maybe not all submarines, but from what I read a bit, on the flanks, you have big antenna panels. In the nose, you have a massive ceramic antenna that's I wouldn't say few hundred kilos, but a few 100 pounds at least, that resonates at very, very low frequency. And I think, if I recall right, it's a few hertz. And again, don't quote me too much on this, but very low in frequency. And because that's the only way you can communicate underwater at high frequencies, the fields will not be able to go too deep, right? But at very low frequencies, it's easier. And then in the tail, usually they deploy a big tail, and I had the chance to see one once. It's a massive amount of metal that is fully, like pieces of metal that are fully mobile. They have this rotation possibility. Each element can rotate freely, and it deploys as far as, I think it's 2 or 3 kilometers to get to the very low frequency range. And the key for that tail that deploys into the water is to make sure that it doesn't make noise when you deploy it. So they not only work on the antenna, but they also work on the whole mechanics, so that when they deploy it, as they move forward, it doesn't make any noise, so they don't get tracked by the enemy. So you have a lot, and again, maybe there is more, but they definitely have the tail, the flanks, and the nose. The flank antennas, I'm not sure what it is. I didn't have the chance to work on it, but the big nose antennas was very impressive. And usually these guys, when they work on those type of antennas for this application, they don't use a chamber like we use today, an anechoic chamber in the air, but it's usually in a swimming pool. So they are very specific, test ranges that are underwater in a lab somewhere, and run tests. So I do believe you can. It's probably not too hard to simulate, as long as the mesh is done very well. I'm not sure if they use today the new tools like HFSS and CST, but a long time ago, we used to use XFDTD. There was Empire. There was FEM, I think, was the very low frequency one for VHF, UHF. So there were tools. I don't know what they use today, but water is not difficult to simulate. A big metallic box is not difficult to simulate. So I believe they do manage to simulate the environment. But as we know, there is nothing that replaces the real test, the real prototype. And for that, you need to also test underwater. And then to get, they don't only have the Submarines antenna system, but they also have relays in a way of buoys or boats, that sucks the power and repeat it to the sky if they have to reach satellites. So, things have evolved since I did that job, a very quick job 25 years ago. But the antennas, designing antennas in a fluid environment is very interesting, and it's
is there a point where you lose communication with the submarine? What kind of range can you get from that, low frequency antenna?
Yeah, so I honestly I don't remember. But you have to be very low in frequency to hear. An example is, you have been diving as well. When you dive, you're underwater at 30 meters down, and you hear the propellers of the boats, and you hear them from pretty far away. So of course it's, you need to check the frequency for that, but it's low frequencies can be heard far away. Waves are also, you can hear them. You never see them, but you hear them underwater. And I don't think it's a very high, it's a high pitch, but I'm pretty sure it's pretty low frequencies. Again, I didn't study whale propagation signals, but I've been diving. You hear them, they are far away, and they do communicate. So.
No, that's a great analogy. Yeah. You even hear a lot of, something hits your air tank or someone else's air tank. You can hear it so clearly, even if they're far away.
Exactly.
Good way to explain.
Is actually the only way you can communicate. Unless you buy, the radio, the mask with the embedded radios. But the only way to communicate, like if I would dive, I haven't dove for a while, but you always dive with a metallic stick to make sure you can click on your tank. Because when something happens, that's the only way. You can try to bubble your way out, but it's really hard.
No point in shouting anyway, right? So, okay, well, look, that was a great conversation, Olivier. I think we could talk all day about it. I think we'll definitely have to do a part 2 of this podcast, because I know for a fact we only talked about even the first probably 1/4 of your career as well, and there's so much more to discuss. But my name's Dermot O'Shea. I'm the host of the Antenna Podcast. You can learn more at our website, theantennapodcast.com. And if you want to contact us, please send me an email at dermot@theantennapodcast.com. And for now, I'd really like to thank Olivier for his time and a great conversation.
Thank you, Dermot, and talk to you soon then.